In our last lecture, we developed the formalism for describing massless bosons and started calculating a bit about the physics. How does this whole thing work? This lecture, we're going to really look much more deeply at the physics of blackbody radiation, and in particular, places where it shows up in the universe and how we can go from this sort of very particular seeming calculations about photons trapped inside of a box to much more general statements about the sun, the earth, you, and so on. In the last lecture, we sketched out the shape of the Planck spectrum for blackbody radiation. To make that a little more quantitative before we head into looking at how different objects radiate, I want to just quickly run through the calculation for finding the peak of that spectrum. In other words, what's the energy of photon that has the highest spectral density? And now just be a bit careful, because you can describe the Planck spectrum in different units, and I don't mean like hertz versus megahertz. What I mean is you can describe it in terms of the spectral density for energy, the spectral density for wavelength. Okay, so to be clear, this U that we found in the last lecture, this is the spectral density per unit energy, right? So this is energy density, right? U over V per unit energy. If you calculate the peak of the Planck spectrum in these units, we'll get a certain answer for various things. If you instead change variables to wavelength, right, there's also going to be a change in the measure of that integral, right? So we got this from taking the integral that gives you energy per unit volume and just pulling out the integrand. If you change that integral to be an integral over wavelength, not only will you substitute in, hc over lambda for the energy, there's also the d energy, right? The measure of the integral. And so you'll actually end up with extra powers of wavelength, which means you will not find the peak in the same spot if you are looking at it as power per unit wavelength rather than power per unit energy. Okay, bit subtle, but you may look at different sources and see different things. And just to add a little extra to that, this is also not the energy window that gives us the most photons, right? This is, again, energy density per unit of energy. In other words, I'm looking in a narrow window of energies. It's the energy per unit volume, U over V, per little bin of energy. So divided by the width of that energy bin. And in a given energy bin, right, each photon has essentially that energy. So at higher energies, the same number of photons would have a higher U over V, or U over V divided by dE, which is our spectral density. Okay, so just a bit of semantics here, but it's important if you start looking at data out in the world for blackbody spectra. Okay, so let's move on. We want to know the peak of this spectrum, okay? Energy density per unit energy, or power radiated per unit density, as we'll see later, per unit energy, as we'll see later. You know how to find the peak, right? Just take the derivative, set it equal to 0. The constants sit out front and don't do anything. We get derivative of the top times the bottom minus derivative of the bottom times the top. Whole thing squared doesn't do anything, because when we set it equal to 0, all that matters is the numerator, right? So here we go, set it up and divide by e squared, because we're going to assume that the peak is not at e equals 0. In fact, if you remember the sketch, the power spectral density goes to 0 as e goes to 0. Which probably makes sense, so that's going to be a minimum. We can ignore that. And now we've got this equation, which we can solve for e to the beta epsilon, but that's not something you can solve closed form. Okay. So you do it numerically. Either you take a few minutes to write some Python code to do it, or you can be super lazy like I was, stick this into Wolfram Alpha, which will not tell you a solution other than 0, and then just type numbers until you get it. Anyway, somehow you solve this numerically, and you find beta epsilon is 2.82. Or, changing this around, epsilon is HF, beta is 1 over KT, so the peak frequency comes at an energy per photon of 2.82 times KT. If you want to get this in terms of frequencies, there's a nice trick to use, which is if you divide by h, you'll have 2.82 T times K over H. And this is a pretty handy approximation for K over H. This is actually quite a good approximation. K over H is, I think to within a few percent, 20 gigahertz per Kelvin. Okay? So if you want to find the peak of the Planck spectrum, you're going to say, what's my frequency? It's 2.8, or if you're being sloppy, it's 3. 2.8 times 20 gigahertz times my temperature, that'll give me the peak of the Planck spectrum. So 20 gigahertz is like kind of mid to upper range of microwaves. And that's at 1 Kelvin. Go up to 300 Kelvin, where room temperature sits, or roughly where room temperature sits. Now you're at 6 terahertz. That's in the sort of very far infrared. That's the kind of spectral peak that we're going to expect for humans. And okay, we can do the calculation a little more carefully. Fmax at 295 Kelvin, what we're calling room temperature, though admittedly you may not keep your room at quite that temperature. 2.82 times our K over H, 20 gigahertz per Kelvin, times our temperature, multiply it out. This is 17 terahertz. And 17 terahertz turns out to be 17 microns in wavelength. And just when I wrote that down, I did a double take. No, frequency and wavelength should not have the same number in them, but square root of 3, which is the speed of light, is 3. So square root of 3 is 1.7. That's why they're both accidentally 1.7 here. Okay, so 17 terahertz, which is 17 microns. And there was a bit of discussion in Piazza about what's the visible range, but visible range is basically 400 to 700 nanometers. So the longest wavelength that's visible is 0.7 nanometers. This is like more than 20 times longer. So this is deep into the infrared. And one of the important points is that in the infrared, particularly this deep in the infrared, most solid objects absorb 100% of the radiation that lands on them. So that will come up later on in the lecture. One of the most interesting instances of the blackbody spectrum in the world is called the cosmic microwave background. Okay. So this is the leftovers of the Big Bang in some sense. The Big Bang, 13.8 billion years ago, the universe begins in this sort of massive expansion of space and time. And about 380,000 years after the Big Bang, pretty cool that we can say these things with multiple digits of precision, about 380,000 years after the Big Bang, the universe is basically a plasma of photons, electrons, and protons. And there's some helium nuclei floating around in there as well, but by and large, it's electrons, protons, and photons. And they're in thermal equilibrium. Okay? Charged particles scatter photons very well, so you've got this sort of dense, hot plasma, temperature of about 3,000 Kelvin. And so, just like in the case of the sun, where your photons thermalize to the plasma, here you have photons thermalized to this plasma that fills the universe. Okay. And at 3,000 Kelvin, this is an important milestone because that's the point at which recombination occurs. And recombination is just what we call it when electrons and protons get together to make hydrogen atoms. Okay. So you remember the Saha equation has sort of a very steep ionization fraction as a function of temperature. So if you look back to your Saha equation, you'll see at 3,000 Kelvin, that ionization fraction is going to really plummet. So we make hydrogen, and hydrogen is not going to interact well with these photons. Okay. At 3000 Kelvin, so we saw that the peak of the spectrum at 300 Kelvin was deep in the infrared, 17 microns. Okay, so at 3000 Kelvin, it's going to be 1.7 microns. That's sort of nearer infrared, but still below the visible. The lowest energy photon that hydrogen will interact with easily is at 121 nanometers. Okay, so deep in the ultraviolet. So there's a huge separation of scales there. Okay, so bottom line, hydrogen's not going to interact with these photons that were present as blackbody radiation before recombination. So as the universe expands, you get recombination, and suddenly you're left with these photons that don't have anything to thermalize with. So that should just leave the spectrum the same forever, but of course the universe is expanding, and that expansion drops the effective temperature of those photons. So bear in mind, they're not thermalized anymore. They don't have anything to interact with to keep them thermalized. There's no bath for these photons anymore. But as the universe expands, you have, your initial L, whatever it was, is going to be expanded by this space-time expansion factor. That leads to two things. One, the number of photons per unit volume drops, not because photons go away, but because the volume gets bigger. Right? So if I've got 10 photons in here and the universe is expanding, now I've got 10 photons in here, number per unit volume is lower. And we can write the energy as HF. We can also substitute for F, right? HC over lambda. The wavelength of the photons also stretches as the universe expands. Okay. So your photon energy, so now if I look at a single photon, its energy is going to drop by that scale factor. So now if you picture that Planck spectrum, we've got e to the beta epsilon in the bottom, right? E over kT. And if the energy goes down, we can preserve that exponent, because remember, these things aren't scattering. They're not rethermalizing. But we can preserve the exponent if we just write this as E over alpha, right? Energy drops by alpha, times alpha over kT. In other words, the shape of the spectrum will fit to a lower temperature, a temperature that's dropped by the scale factor of the expansion. Similarly, we've got U over V, right? If N over V dropped by 3 powers of the scale factor, and the energy per photon dropped by 1 power of the scale factor, then this energy density, right, energy per unit volume, will drop by 4 powers of the scale factor. 1 from here, 3 from here. Energy per unit volume is exactly scaled kT to the 4th. So this also looks like the same energy density, just at a temperature that's alpha smaller. So you put this all together, what started as blackbody radiation at 3000 Kelvin today looks exactly like blackbody radiation, both in terms of spectral shape and energy density, but blackbody radiation at 2.7 Kelvin. So this allows us to look back in time to less than 400,000 years after the Big Bang. The cosmic microwave background, it's essentially the most perfect blackbody spectrum that's ever been measured. So I just wanted to show you a couple of quick bits of the data. This is the spectrum measured by the Kobe satellite, which actually flew decades ago. This is not at all the most advanced satellite that's been sent. This is the spectrum that it measures for the cosmic microwave background. And the uncertainties in the plot are smaller than this incredibly thin line that they've used to plot the data. Okay, so this just fits to a blackbody spectrum phenomenally well. You can extract the temperature as 2.726 Kelvin. It's that good. In fact, it's so good that more recent satellites, like the WMAP, Wilkinson Microwave Anisotropy Probe, and the Planck satellite from the European Space Agency, these satellites don't even bother to publish a plot like this anymore, really. They're like, you all know it's a nearly perfect black body. The only thing that's interesting is the deviations from it being a perfect black body. And in particular, they show plots like this. So this is from the website for the Planck satellite. And what you see, this is the temperature anisotropy. So in other words, I look this way, I measure the black body spectrum. I look this way, I measure the black body spectrum. I look that way, right? So what's the effective temperature in each direction that I look? And then they make sort of an all sky plot of this. What's this horrible stripe in the middle? That's the plane of the Milky Way. Can't take data when the Milky Way is radiating at you. But once you look off plane, you can measure these things. And the scale here is 100 microkelvin. So the absolute biggest shifts that they see are 100 microkelvin, whereas the background temperature, 2.7 Kelvin. Okay. So even the deviations from isotropy, from being the same temperature in every direction, these deviations are very small. And in fact, what I said about look this way and measure, look that way and measure, it's not what they do. They look two ways, compare what comes in, and just measure the difference, because sort of it's such a sensitive measurement. It's better to measure the two simultaneously and compare them. Okay. Getting into details, but the main point here is that these fluctuations tell us something about the density fluctuations in the early universe. And those density fluctuations lead to the formation of a large-scale structure in the universe, right? If there's a little bit higher density over here, that may eventually collapse into a galactic cluster, right? That's a pixel here is on that kind of size scale. And in fact, what they generally will publish, even these look great, the meat of the data isn't something like this. This looks at the distribution of those temperature fluctuations as a function of multipole moment, which has some connection to the things that you did looking at the hydrogen atom and quantum mechanics in terms of spherical harmonics. But if multipole moment doesn't sound intuitive to you, angular scale is just as good a way to think about this, really. So you can see it's a bit noisy. What's the fluctuations down here at these sort of larger angular scales? But as you get to smaller scales, you get this fantastic curve. These fluctuations tell you a lot about the density of the universe, lead to answers about structure formation type things. So there's a ton of information in this, just in the tiny deviations from being a perfect isotropic black body. We started the whole discussion of massless bosons by thinking about photons inside of a cavity, right? I've got a box full of photons, but I don't care about photons inside of a box, right? Like, I can't see them, they're in a box. So how we go from that consideration to things like how much radiation do you give off, okay? Or the Earth, which we'll talk about in a little bit. That's important. That's what gives a lot of the importance physically to these calculations about black body radiation. So I just wanted to motivate that, and then we'll work our way through the calculation. So if I've got my photons in a box, I've got some energy density inside the box. Hooray for anything inside the box. There's some energy density there. If I poke a hole in the side of my box, like so, now that energy density can escape, okay? And there will be a P for power, not pressure, although there's also radiation pressure, but what we're going to be concerned about is the power that radiates out, right? That's very analogous to energy density, right? This is energy per volume, okay, so length cubed. Power is energy per unit time, And what we're really going to care about is power per unit area. So this is energy over length cubed. Power per unit area is energy over length squared times time. Okay, so the difference is basically a velocity, which you'll see as we finish the calculation. Okay, great. If I've got a box full of photons and I poke a hole in it, we will figure out how to calculate the power that comes out. We can turn that into a power per unit area. Still, I'm not generally running around with boxes full of photons and like poking holes in them to let the photons out. So where this really becomes important, and in fact where the name blackbody radiation comes from, is the idea here, which as I look at it now, I hope you can make this out. I've drawn a little gray guy, but of course on a black background, drawing a black body is not the best thing. Well, okay, I think you can see it. There's a little box that I've drawn here, which is gray. So after I poke a hole in my box full of photons, I'm going to hold something up to them, right up next to the hole, that absorbs all the light that falls on it. Okay. So if the box full of photons is at some temperature T, and I have a perfect absorber of electromagnetic radiation, and I hold it right next to the hole in the box, that thing should, once it comes to equilibrium, be the same temperature as the photons inside the box. And there's sort of a very nice thermodynamics argument for that. If that thing were at higher temperature, sorry, I should step back, should be at the same temperature and should radiate the same spectrum. Okay. So that's the important thing. If this black object, okay, black because it's absorbing all of the radiation incident on it, this black object absorbed more of the light than it emitted, then it would continue to heat up, sort of, forever. So that tells you a perfect absorber has to also be a perfect emitter. And now if it emitted a different spectrum, right, so if this thing emitted a different spectrum back into the box, well, if it was a spectrum with less power density, then the box would be getting less energy back than it sends out, and it would be cooling. Okay. If this thing had a power spectrum that was higher energy density, then it would be heating up the box. Okay. So at the end of the day, this perfect absorber right next to the box is going to have exactly the same spectral emission at the same temperature as the box. Well, there's nothing special about the box being right next to this, right? That's a thermodynamic argument that tells you something should happen, but it doesn't require that the box be there. If I take the box away and I just have a perfectly absorbing and perfectly emitting object, remember, those two go hand in hand. Absorption and emission have to have the same, level. Then an object at a certain temperature will radiate exactly like a hole in a box full of photons. Okay. So we're going to calculate what comes out of a hole in a box full of photons because that's a straightforward calculation to put together. But by this thermodynamic argument, we know that any object that has perfect absorption and emission of radiation, that will also radiate the same spectrum. Good. So let's do the calculation. All right. Got my box, poked a hole in it. At any given time, we can think about sort of a hemispherical shell, right? Half of a sphere centered on the hole, or centered on the center of the hole, because our hole is going to have some area. All of those photons have a chance to get to the hole at the same time, right? If a photon in this hemisphere is pointed at the hole, it'll get to the hole at the same time a photon from this part of the hemisphere gets to the hole. And so we'll just call this thing's radius r. If I look at a small wedge of this, of a very small azimuthal angle, polar angle. I keep saying these backwards. If we look in a wedge of small polar angle, so I'm measuring from the center line upward, this little thing has width r d theta. And if I now want to take care of the azimuthal angle, I'm confused because my pole points this way, right? Usually your pole points vertically, now my pole points this way. This is my polar angle. My azimuthal angle is circling around this horizontal axis. Azimuthally, this hemispherical shell should look identical all the way around. Okay? So really I can think of my polar angle, right? It's my tilt downward away from the axis. My hand goes up because normally I think this is my pole and I'm tilting downward. So here's my pole. I tilt a certain amount away, azimuthally all the way around. So here's my axis. Azimuthally all the way around that axis at a given theta, the thing is identical. That's a circle whose radius is r times sine theta, right? There's your theta, r sine theta. So now what I want to know is how much energy is in this hemispherical shell. Okay. Well, in this little bit, once I rotate it around to make it an infinitesimal ring, I get 2 pi r sine theta, right? So the radius of this circle is r sine theta. 2 pi times the radius of the circle is 2 pi r sine theta. Then the cross section of the circle is this r d theta times dr. Okay? R d theta times dr. That's the volume I have, and we know, because we've calculated photons in a box a lot now, there's a constant energy per volume. So energy per volume times our volume gives us our energy. So that's the energy contained in this hemispherical shell. And I'm going to use this. dr is c dt. In other words, I picked this shell because I want to know how many photons arrive in a given infinitesimal time period. And that number of photons will be, well, the width dr divided by the speed of light. That's how many photons fit in there. Okay. So I'm just going to change the dr into a c times dt. Okay, so that's how much energy is in this spherical shell. Next question, how much of it gets out? Okay. Oh boy, I've got another P. This is now P for probability. If I just look at my little infinitesimal box here and ask, how many of these photons are going to go out? Okay. Well, the answer is essentially photons in this little box go in any direction with equal probability. So how many directions lead them out of the box? If we take the area of this hole, so now we're going to be looking at the hole from the perspective of our infinitesimal little chunk. Whereas before we were doing the opposite, right? We're from the hole and we're looking out at the infinitesimal chunk. Now, do the reverse. So from this little chunk, if I look back at the hole, it has an area A, right? But I'm looking from here. So I don't see the whole area A. All I see is the projection of the area onto my line of sight. And that projection is smaller by cosine theta, right? So if my chunk is at theta equals 0, it sees the whole dead on, it sees the whole area. As it goes up, it sees less area by cosine theta. If it was right next to the wall, right, you can't see the hole at all, well, that's pi over 2, cosine pi over 2 is 0. Okay, so this all should make sense. So the probability that it gets out is the projected area of the hole divided by 4 pi r squared. In other words, in any direction it could have gone for the same distance as the distance to the hole. Okay, so this is turning this into sort of a solid angle. What's the solid angle? And really we're saying the fraction of a total solid angle. So the probability looks like so. dE we had, but now instead of the dE being the energy in the shell, we're going to say the dE is the energy that gets out of the hole at some time R over C later. Okay, so we're going to take the dE that was in the shell, right? Bring it down. So here's the non-theta parts. Here's the theta and t parts. Then we'll bring the probability in. And hey, 2 pi's and r squareds, everything's canceling. This is great. So we end up with U over V, our energy density, times C, times the area over 2, area of the hole again. Picked up a cosine theta. We already had a sine theta. We got some differentials, so we're going to need to do an integral in a second. The physical quantity I care about is not the energy in some infinitesimal time. I care about the rate at which energy leaves the box, and in particular, the rate per unit area, right? So if I poke a tiny hole, what's the power that comes out? If I poke a larger hole, the power that comes out should be larger, and it should be larger in proportion to the area. We see that. So rather than having to redo this, all the time and not be able to say something very universal, if we look at the power per unit area, we're going to come up with a very general rule. So that's our quantity of interest. Power radiated per unit area. Why is this going to be so general? Well, look, A is the only thing left over here that has anything to do with my box or my hole or anything, right? The R, this sort of imagined radius for the spherical shell, disappeared, canceled out. If we get rid of the A, there's nothing over here but the energy density of a black body, which was something we calculated long before we thought about poking holes in boxes, the speed of light, and some angular stuff that'll go away when we do an integral, right? So divide by A, divide by dt to make it the power, and all that's left, C over 2 times the energy density. Here's the angular stuff. Great, let's integrate to get rid of that. So rather than the power from a certain angle, we're going to get the total power, right? Because it still depends on theta, secretly what I've got here is power per unit area at a specific angle. When we integrate over this, we get over all angles. Great, we can do this integral, right? 0 to pi over 2, because we just get half of the sphere. Cosine theta times sine theta, the integral turns into just an integral du of 1 from 0 to 1. It's a half. So drop the half in here. Our final answer, so the total power density that's radiated, and I was a little careless here. These should not be equal in the sense that up here we're looking at the power density. Here, let me make a note. This is important, and I was being sloppy. This is, oh, I'm writing vertically again. All is lost. Okay, so this one is the power density, power rated per unit area, for a specific theta. Okay. Wow, theta is shaggy somehow. Let's try that again. Oh, I see what's happening. This is why we don't write on vertical surfaces. Okay. Whereas this is the total. The total is what we really care about. Okay, good. So slightly wiggly, but now you know what's going on sort of more carefully. So total power per unit area, we have a nice simple formula. And I kind of hinted at this earlier when I talked about the units for these things, right? Power per unit area, it just looks like an energy density times a speed. Easy enough. Okay. I'm going to also refer to this as the energy flux. Okay. So it's the energy that leaves through a certain area in a certain time. We can plug in our u's and our expression for u over v, right? 8 pi to the 5th over 15, kt to the 4 over hc cubed. Collect this all up, pull the t to the 4th out, because everything else is a constant, right? Speed of light, Boltzmann's constant, Planck's constant, another speed of light, some pi's. Wrap all of that up together and refer to it as sigma. Okay. This power flux equals sigma t to the fourth. This is Stefan's law. Actually, we'll write it slightly differently in a moment, but this is Stefan's law. And this constant is called the Stefan-Boltzmann constant. Okay. So when you put all of these in and chug through the numbers, 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Funny looking unit, right? But if you put it in, you see it does the right thing. It gives you watts per square meter. And I said we'll write the Stefan law slightly differently in a moment, which is rather than looking at the flux, looking at the total power. That just means we put the area on the other side, right? So total power radiated is area times the Stefan-Boltzmann constant times t to the 4. And so I said, great, let's calculate my black body emission. Okay. So this is going to be very schematic order of magnitude type calculation. I said T human's about 300 Kelvin. If your actual temperature is 300 Kelvin, see a doctor, right? You should be about 310, but fine. For our purposes, we're not going to worry about the few percent that's off. Just like the surface area of a human is probably not 1 square meter, but it's not 10 and it's not a tenth. We just want to get the right ballpark figure here. So how much power do we radiate? Well, just put it into the formula, right? About a square meter, Stefan-Boltzmann constant. Hey, look, I'm not bringing 3 digits if I'm approximating a human as 1 square meter. So we'll just put the 6 in. 10 to the minus 8 watts per meter squared Kelvin to the fourth. Again, funny unit, but the meter squared cancel and the Kelvin to the fourth cancel and you get watts. Good. 300 Kelvin to the fourth. Well, 3 squared is 9. That's about 10. We're going to do it twice because it's to the fourth. So that's 2 powers of 10. 10 squared to the fourth is 8 powers of 10. So we've got 10 powers of 10. Cancel that there. 600 watts. It's an awful lot of power for you to be radiating. Do you feel okay? Okay, so that's not your total power loss though, right? Because just as you're radiating black body radiation, your environment, which is at a slightly different temperature, is radiating black body radiation into you. And again, this is important. If you are a perfect emitter at a certain wavelength, you're also a perfect absorber. And we saw at these sort of room temperatures, we're in the far infrared. That's where the spectrum peaks. Human bodies are pretty perfect emitters and absorbers at these wavelengths. Most anything around you is. Okay, infrared gets into vibrations for solids, and solids have all kinds of internal vibrations possible. So essentially, you're a black body, at least at the infrared, which is what counts. So T to the fourth minus, right? So this is your radiation minus T minus delta. In other words, my environment is not at the same temperature as me. To the fourth. Delta should be much smaller than T. So we can just take the first order approximation here. And we get 3T cubed times delta. Okay. Well, okay, now I care about the difference between a human being at 300 and 310 Kelvin. So let's say the difference between you and your environment is about 15 Kelvin, right? So if I'm at 37 Celsius, my environment's at 22 Celsius, that's a difference of 15 Celsius. And since we're using Celsius, that's also Kelvins. Great. So why did I only do this? I left off the A and the sigma because I just want to know the fractional change. So delta P, which would be proportional to this, over P, which would be proportional to T to the 4. This is just your 3T cubed delta over T to the 4. So you just get 3 delta over T, which is to say this will give you a 15% of what you started with, right? So only 0.15 times 600 watts, that's your net power loss due to radiation. Multiply that out, that's only 90 watts. It's good news that this is 90 watts instead of 600 watts. Hope that wasn't behind my head. Delta P is 90 watts. Why is it good news? So a food calorie, bit tricky. Food calorie has a capital C because it's actually a kilocalorie. So you may have learned in your chemistry courses about little c calories, and I'm sure they told you about kilocalories and big C calories too, but a little c calorie is like the energy needed to raise 1 gram of water by 1 degree Celsius at some particular reference temperature. I forget, but it's kind of a normal one. That comes out to be about 4.2 joules. So 1 food calorie with a capital C is 4.2 kilojoules. Average diet's supposed to be 2,000 calories a day. Multiply it out, 8.4 megajoules. Okay. If you're losing 90 watts to radiation, and a day is about 86,000 seconds long, that's about 90,000. 9 times 9 is 81. So that's 8 megajoules. Okay. Hey, that's how many you ate. Okay. If this was 600 watts and we weren't getting radiation back from the environment, that'd be real bad. We'd be, radiating away, well, what is this? About 7 times more radiation than we eat on a 2,000 calorie diet. Now, that small difference there, this is not like the key to your life. Obviously, you don't sit as a perfect radiator in your room. You wear clothes, you have, hair and things. So you're not actually losing 90 watts all the time as blackbody radiation. And in fact, the bigger cooling mechanism for temperature differences this small is convection. So the biggest reason to have little hairs and clothes and so forth is to stop convection, right? Convection is when a fluid, which the air in your room is a fluid, it conducts and then flows away, right? So some air next to my arm is going to pull heat out of my arm, and while it's pulling the heat out, it's also moving away. That's a super efficient way to cool things. So that's the biggest thing that we need to stop. And holding on to blackbody radiation, it's a good bonus. We want to do that too. Okay, last comment to make about blackbody radiation in this context is that the power radiated, we said A sigma T to the 4. There's something else we need to include when we want to talk about how this happens in the world, which is this emissivity. Emissivity is what fraction of light is absorbed. Okay. And as I already hinted, this depends on the wavelengths or frequencies of radiation that you care about. Again, I say light all the time, but in most of our contexts, we're really talking about far infrared or microwaves, not visible light. Okay, so if I set an object out, I shine a certain power on it, the fraction of that power it absorbs is its emissivity. And we talked about the fact that by this thermodynamic argument, those have to be the same, right? If I could absorb more than I emitted, or a greater fraction than I emitted, then I could sit next to a perfect emitter and I would slowly heat up. But I'd heat up forever, even after my temperature passed the temperature of the emitter. That violates the second law. Similarly, if I could emit more than I could absorb, then I would sit next to a perfect emitter and I would slowly cool down even until I was lower temperature than that perfect emitter. Again, you'd have another violation of the second law, right? Basically, I'd be emitting more into the emitter even though I was at a lower temperature. So you have heat flow from a low temperature to a high temperature. Okay, so those arguments, again, simple thermodynamic arguments that tell you emitted fraction has to equal absorbed fraction, which is why this thing that I defined as the fraction of light that's absorbed is called the emissivity, because that's also the fraction of light that's emitted. Okay. So that ends up just being a straight conversion factor that goes out front. So all the physics we've talked about is the same. It's just that your emission and absorption may be imperfect. And if they're imperfect, then again, emission and absorption are imperfect to the same extent. And with that, we can calculate the power loss for most anything in the world. We just have to have some measurement of its emissivity. Now, this last section, I thought about holding to the next lecture so that this one didn't get too long, but the concepts here are pretty straightforward, and I think you'll enjoy getting this last bit about blackbody radiation. So global warming, it's not all bad. This is, just to be clear, not a statement that I grew up in Florida, so I think the whole Earth should be a hot, muggy swamp. Although, maybe. But no, that's not what I'm getting at. You'll see in a moment that the Earth needs some amount of global warming to be the temperature that's sort of hospitable to life. It's not all bad, but you can have too much of a good thing, except coffee. There's never too much coffee. Okay, so we have the sun. It's emitting electromagnetic radiation. We have the Earth. It's receiving some of that electromagnetic radiation. And this solar insolation constant, I for insolation, 1.37 kilowatts per square meter. That's the incident power density at the Earth's distance from the sun. So the Earth's temperature is pretty constant. Maybe it doesn't feel like that day to day, but when you average over the globe, the Earth's temperature is pretty constant. So we must be in some steady state. And if we're in a steady state, that means that the power in has to equal the power out. So this ends up being a simple application of Blackbody and Stefan's law. Okay. So power in is this insolation times the cross-sectional area of the Earth facing the sun, right? So you can think of the Earth as just a circle receiving radiation. You could think of it as a hemisphere, which gives you a factor of 2 out front. And when you take account of the effect that, the angles aren't always head on, your 2 is going to cancel. And you'll say, gee, why didn't I just treat it as a circle to begin with? That was a lot of integration for nothing. So treat it like it's just got its cross section, pi r squared times the insolation constant. And that equals, whatever power the Earth radiates depends on its temperature. And you can see I've set the emissivity to 1 because, again, solid objects at temperatures in the couple hundred Kelvin have emissivity very close to 1. So A sigma t to the 4. What's our A? Now we need the total area of the Earth, right? Because we're assuming that the Earth ends up thermalized and then radiates into space in all directions. So now we need the total surface area of the Earth, 4 pi r squared, sigma t to the 4. Just solve for t to the 4, right? All the pi's and r squareds go away, I over 4 sigma. And we get a t to the 4th of 6 billion Kelvin to the 4th. Okay, take the 4th root. T is 279 Kelvin. So just based on the power balance, power in from the sun equals power radiated by the Earth, we come up with a temperature of 279 Kelvin, which is 6 Celsius. Now, if the average temperature over the Earth's surface over the course of the year was 6 Celsius, I don't think we'd be terribly happy. Right? If we all got that average, maybe, but realistically, we know Canada's going to be colder than the equator, so the actual average over the Earth is more like 15 Celsius. So I don't know about you, but I don't want to drop the average temperature here by 9 degrees. That sounds sad. Okay. So we're missing some physical effect. The most important physical effect is clouds, right? My little drawing of the Earth here. It's a sunny day everywhere. Not always true. There are clouds. And clouds reflect the incoming solar radiation, right? So the sun is emitting, its peak is in the very near infrared. So a lot of that radiation is in the near infrared and visible, which clouds reflect really well. So cloud reflection drops that insolation factor by 30%. 0.7. If you take the fourth root of 0.7, multiply it by 279, right? Because that's all it's changing, is the numerator up here is changing by 0.7. This gives us a global average temperature expectation of 255 Kelvin. And for reference, so far this year, the minimum temperature in Waterloo, yes, native Floridian, I watch these things closely, 256 Kelvin. So in fact, this would predict the average temperature of the Earth is a degree colder than the coldest it's been so far in winter here. That would be very inhospitable to life. For example, all of the water would be frozen, always. So this is why I said greenhouse effect, it's not all bad, okay? Something needs to raise this temperature, and it is in fact the greenhouse effect. So one point about the greenhouse effect, it's not actually how a greenhouse works. I assumed that it was how a greenhouse works for years, and then got into a very unfortunate conversation about greenhouses. So this is not how greenhouses work. The way a greenhouse works essentially is it insulates you against convection, but allows all of the radiation in. So there's a relation, which is that the atmosphere lets all of the sun's radiation in. The difference is that in a greenhouse, the dominant cooling effect that you're blocking is convection. And as I said a little earlier, convection is much more efficient than radiation for cooling things at normal sort of room temperature scales. Okay, that's an aside about greenhouses. Great. So the greenhouse effect, it happens like so. I'm going to have the Earth's surface, which is a more or less perfect absorber of the sun's incident radiation, and the atmosphere, which is essentially transparent to the Earth's incident radiation. So, not to the Earth's radiation, sorry. The atmosphere is essentially transparent to the sun's radiation. So the sun's radiation passes through the atmosphere, hits the surface, gets absorbed. All that power turns into thermal energy in the Earth's surface. The Earth has some temperature, so it radiates back, but it radiates back at much longer wavelengths, right? We said it's like 17, 20, something like this, microns is the peak at the Earth's surface temperature. So these long wavelengths, the atmosphere does absorb really well. Okay? So I wrote this E of F over here because in reality, emissivity is a function of frequency. So the Earth's surface absorbs well at all of these frequencies, infrared, far infrared, visible, whereas the atmosphere absorbs extremely well in the far infrared, not very well in the near infrared, not at all in the visible. The fact that the emissivity of the atmosphere in particular is a function of frequency is what makes the greenhouse effect work. Okay. So now let's look at the power balance. On the surface, the power re-radiated by the surface has to equal the power that comes into it, which is the full solar insolation plus, and here I've made this super cartoony thing where the atmosphere is a single sheet. Okay, it's a perfectly absorbing in the far infrared sheet, which also happens to be transparent in the visible. So half of its radiation goes up, half of its radiation goes down. So the surface gets the full solar insolation plus half of the power radiated by the atmosphere. And the atmosphere, it's got its output, and the only place it's getting pumped by is the re-radiation from the Earth's surface. So the power radiated by the atmosphere must equal the power radiated by the surface. Okay? Just solve these equations, right? You get PA is I plus a half PA. So PA is twice I. It's twice the solar insolation. So the atmosphere is re-radiating twice the power. And if we plug in 2I here, right, we get I plus I. Earth's surface is also radiating twice the power. However, the only thing that escapes back into space is the upward emission from this perfect sheet of atmosphere. So in other words, PA over 2 is what's re-radiated into space. So the overall power balance for the system also makes sense. You've got I being input by the sun. You've got I being emitted into space by the atmosphere, and then there's sort of a radiation exchange between the Earth and the sheet O atmosphere. Okay. So that works out, gives you the right power balance. Now what's going to happen? Well, just like up here, the clouds made it 0.7. This is now, I should say this I is 0.7 times I, right? This is the I that makes it through reflections from the clouds. Okay. So I'm going to take now my 255 calculated with cloud reflection taken into account, and I'm going to have double the power coming in. So let me be clear. I'm going to call this I prime. And again, I'm writing on a vertical surface, but I think I can make a dash. Yeah. Okay. Great. So I prime the power that gets through the clouds. So I take the fourth root of 2, multiply it by 255, right? And I get 303 Kelvin. Okay. Average temperature over the Earth's surface is 30 Celsius. That would also be bad. Not for Canada, but for Florida. So again, real answer is 288 Kelvin. So this has all given you maybe the sense that we have no idea what we're doing. No, this is sort of encapsulating the important effects, right? Sun's radiation hits the Earth re-radiates. Some of the sun's radiation doesn't make it to the Earth because it's reflected by clouds, but the radiation that hits the Earth and is re-radiated is trapped by the atmosphere. So this all adds up to give you the real answer. Now, why are we off by so much here? This is really a cartoon model, right? The atmosphere is a single sheet hovering above the Earth, absorbing and re-emitting. You can actually make just a slightly less ridiculous model and nail this number almost spot on, which is don't make it a perfectly absorbing sheet. Break it up into 2 sheets with 50% emissivity. And then you get essentially the right number here. Of course, you should do much more complicated things if you're a climate scientist in calculating this, but one thing you get from breaking it into 2 sheets with emissivity of 0.5 is that you can now model what happens if the emissivity goes up a little bit, right? So that's what adding CO2 and methane to the and water vapor as well to the atmosphere, that's what that does. It changes the emissivity a bit, and you can see that there is actually a strong leverage there. A small change in emissivity will make a big change in the final number. And so that's where we get a little goes a long way, a little extra can actually be quite bad. That sounds like a really great homework question.